Can I start?
Yeah, please do.
Okay. Yeah, so welcome to this talk. And today I will talk about large surgery formula for instant and floor homology. And this is a joint work with Zhengkun Li. So first, let me sketch the idea of this talk. So it is well known that there's a knot floor chain complex CFK infinity, and we can use this chain complex to calculate Higgs floor homology HF hat of the M surgery of K. So usually if M is large enough, it is called the large surgery formula. And for instant and floor homology, there's an analog construction KHI which correspond to the knot floor homology. But there's no differentials on KHI. So in this talk, I will mention how to construct two differentials D plus and D minus on KHI, which are analogs to DW and DZ on CFK infinity, and then use them to calculate I sharp of the M surgery for large M. And this is based on the conjecture of Kroheimer-Morovka, which says KHI of K is isomorphic to HFK hat of K, and I sharp of Y is isomorphic to HF hat of Y. And for instant and floor homology, Bodeman and Civic says if the dimension is larger than the order of the first homology, then we have some existence of irreducible SU2 representation for pi 1 of Y. And then let me start now. So then let me quickly review the instant and floor homology and Higgs floor homology. So first, suppose Y is a closed ring manifold and omega is a Hermitian line model. Then floor constructs a version of instant and floor homology, which we denoted as I omega of Y. And later, for a balanced suture manifold M gamma, Kroheimer and Morovka constructed suture instant and homology, which we denoted as SHI of M gamma. So here M is a 3-manifold with boundary, and gamma is a one submanifold on the boundary with some balance conditions. And for Higgs floor theory, if we consider a closed 3-manifold Y, then Auschwitz and Szabo constructed Higgs floor homology. There are 4 versions of Higgs floor homology: hat version in infinity, plus and minus. And for a knot in a closed ring manifold Y, Auschwitz and Szabo and independently Rasmussen constructed knot floor homology HFK, and there are also 4 versions of them. And for balanced suture manifold, U has constructed sutured floor homology SFH of M gamma. So there are many notations. So maybe let me sum them up in a table. So in this talk, we will consider the suture manifold M gamma, and in Higgs floor homology, it is denoted by SFH. In instant and floor homology, it is denoted by SHI. And we will consider a knot in a closed ring manifold and take the 3-manifold to be the knot complement and take the suture to be 2 meridians of the knots with different orientations. In Higgs floor homology, we use HF hat. We use HFK hat, and in instant we use KHI. For a closed ring manifold Y, we take the manifold to be Y minus the 3 ball, and the suture to be a connected curve on the boundary. Then in Higgs floor homology, we use HF hat, and in instant we use I sharp. So well, this is a little different from the I omega I mentioned before. This is another version of instant and floor homology. Okay, and then there is a conjecture by Kroheimer and Morovka, which says for any balanced suture manifold M gamma, we have an isomorphism SHI is isomorphic to SFH. So in particular, we conjecture that KHI is isomorphic to HFK hat, and I sharp is isomorphic to HF hat. There are many examples that this isomorphism is already be proved. So for example, KHI is isomorphic to HFK hat for alternating links in S3, all torus knots, and all 1-1 Lspace knots and all constraint knots in Lspaces. Well, these are just some families of 1-1 knots in Lspaces, and there are many works by Zhengkun Li and I, and also Baldwin. Okay, and for closed ring manifold, we have the isomorphisms iSharp with HF hat for double branch cover over an alternating link, and the surgered manifold for a knot K admitting Lspace surgery, and cipher fiber rational homology spheres, and also the strong Higgs floor Lspaces. So the definition of strong Higgs floor Lspaces is just the dimension of HFK hat equals to dimension of the Chen complex, which is also equals to the order of the first homology. That's the definition. Okay, so and then maybe let me mention the large surgery formula for Higgs floor theory, and then state the main theorems. Okay, so so here let's just consider a knot K in S3. So just as usual in Higgs floor theory, we take a doubly pointed Higgs diagram and consider the Chen complex CFK infinity, which is generated by Xij, where X is the intersection number of the intersection points of T alpha and T beta, and Ij are two integers satisfy this condition, and Ax is the Alexander gradient. So the differential looks like this, just obtained by counting holomorphic disks. And then so the followings are examples of the trivial. So for the trivial, we have 3 generator in T alpha intersect with T beta, and then we can draw the Chen complex like this. Okay, and then we define the band complex to be the generator and differentials in this region for -1, and in this region for 0, and in this region for A1. So that's the original definition for band complex. And indeed, we can also define it just by intersection points in T alpha and T beta. And if we can just consider the differentials dz and dw associate two base points z and w, and define the differential to be dw if the Alexander gradient is larger than s, and dz if the Alexander gradient is less than s, and dw plus dz if the Alexander gradient equals to s. So this is another definition for the band complex, and this is the subcomplex associated to dz, and this is the subcomplex associated to dw. Okay, and the reason to introduce the band complex is the following theorem. So this is the large surgery formula by Oshvason, Zabel, and also Rasmussen. So it says that for a large integer m and integer s satisfy this condition, then the surgeon manifold, the HF hat of the M surgery in some spin C structure could be calculated by the homology of the band complex. So this is so in this theorem we can find that we can calculate the band complex. We can calculate the M surgery by the band complex, and indeed we can also calculate the plus version of the M surgery by other band complex. But in this talk, we will only focus on the hat version. Okay, and so my work with Zhengkun is just to construct two differentials d plus and d minus on KHI, and so that the homology of these two differentials are isomorphic to I sharp of the ambient three manifold S3. And then if we define the band complex just similarly by replacing dw by d plus and dz by d minus, and then we get an isomorphism between I sharp of the M surgery and the homology of the band complex. So here note that a priori there's no spin C decomposition for I sharp, but indeed we can find some spin C-like decomposition for I sharp so that this special component is isomorphic to the homology of the band complex. And also maybe you can find that in the statement there are some minus signs, and this minus signs means we take the mirror manifold. And the reason is because we will use some contact gluing maps to construct the differentials. And moreover, we can prove the following theorem, which is already shown by Oshvatz and Szabo in Higgs theory. So first, let me introduce the definition of instanton Lspace knot. So the definition is that so there exists a surgery slope R so that the dimension of the I sharp of the R surgery equals to the order of the first homology. And then this knot is called instanton Lspace knot. So the theorem by Zhengkun and I says if K is an instanton Lspace knot in S3, then the dimension of KHI in each Alexander grading is either 0 dimension or 1 dimension. And moreover, the Z mod 2 gradings of the generators of the one-dimensional space are alternating. So we can use this fact plus the Euler characteristic theorem to get a constraint on the Alexander polynomial. So which means for an instanton Lspace knot, the Alexander polynomial must look like this. So this form, we can write it out, just looks like t to the nk minus t to the nk minus 1 plus t to the nk minus 2. Just the polynomial looks like this. And indeed, our proof is also analogous to Oshvatz and Szabo's original proof, and it also used the large surgery formula I mentioned before. So for the large surgery formula, and so the reason to study instanton Lspace knots is because the following facts. So first, we have a proposition that the dimension of I sharp of the R surgery is always larger or equal to the order of the first homology. So if K is not an instanton Lspace knot, which means for any R, we don't have equality here. So which means for any R, we have the dimension is larger than the order of the first homology. Then this means the fundamental groove of the R surgery will have a irreducible SU2 representation in the following cases. So the first case is well, this holds for all but finitely many slopes R, and this is a result by Civic and Zettner. And the second case is that if R is P over Q and P is a prime power, then this fundamental group always has a irreducible SU2 representation. So this is effects by Baldwin and Civic. And we can use this. We can use the criteria to find that some knots are not instanton Lspace knots. So, for example, hyperbolic alternating knots are knots, and Monsignor knots in particular are Pareto knots, except some torus knots, and Pareto knots are always not instanton Lspace knots. And the third family is the knots that are closures of 3 braids, with some exceptions. Well, these are twisted torus knots. So we can use this fact to show that for a knot here and a surgery slope satisfy this condition, then the fundamental groove must satisfy the must have irreducible SU2 representation. So, and indeed, we can use the large surgery formula and constraints on Alexander polynomial to prove a stronger theorem. Well, so recently, Baldwin, Lee, Civic, and I shows that for any non-trivial knot in S3, the fundamental groove of the 3 surgery has irreducible SU2 representation. So there are many other inputs for this theorem, but the constraint on Alexander polynomial for instanton Lspace knots is one of the important inputs. So these results correspond to Kroheimer and Morofka's results for the slope in 0 and 2. So and later Baldwin and Civic also proved the existence of SU2 representation for slope 4 and many slopes in 2 and 3. And indeed, our theorem can be generalized to slopes in 4 and 5 and an interval in 3 and 4. So this is another important application of the large surgery formula. And finally, there's a theorem in preparation by Zhengkun and I, which says we may calculate I sharp of any integral surgery by the differentials d plus and d minus. And we expect that the formula will look like the Auschwitz and Szabo's mapping cone formula for HF hat. Okay, so is there any questions for these theorems? Okay, so maybe then let me go to the next part, and I will introduce the analogs constructions in instanton and Higgs-Floor theory. So first, let me review the notations of Higgs-Floor theory and instanton theory. So for the floor homology, we have SFH for the balance suture manifold, and HFK hat for a knot in a 3 manifold, and HF hat for a closed 3 manifold. And here we also have SHI for balance suture manifold, and KHI for a knot in a closed 3 manifold, and I sharp for a closed 3 manifold Y. And there's homological grading on either homology. So for Higgs-Floor homology, it is called Maslov grading, and usually it is the Z grading. And for instanton homology, we only have relative Z-mod 2 grading, but this is enough because we can take the Euler characteristic and say something about it. And indeed, we also have another grading which we usually call Alexander grading. So in Higgs-Floor theory, we can define it by considering the first Chern class of the spin C structure and pairing it with the surface S. And in instanton, we can consider the operator mu associated to the surface S and consider the eigenspaces. And then for either theory, we have a surgery exact triangle, which I will state detailedly. Okay, so here is the most general statement for the surgery exact triangle. So let's consider a knot in K in the interior of 3 manifold. So here the 3 manifold M could have some boundary. And then we consider the balance suture manifolds Mi, gamma I, which are obtained from the original balance suture manifold M gamma by dense surgery along K with slopes satisfying this condition. And then there exists a long exact sequence between SHI of these balance suture manifolds. So in our special case, we should consider the following balance suture manifolds. So first, we still consider a knot K in S3, and we consider M to be the knot complements. And we suppose mu and lambda are meridian and longitude of K. And then we take the suture gamma n on the boundary of M to be the suture consisting of 2 curves of slope minus n. So here minus n means the homology class of the curve is just minus n mu plus lambda. If we push the meridian mu into the interior of M and to get the curve mu prime, and considering the framing induced by the boundary of M, then the surgery exact triangle on mu prime will give us the following exact triangle. So this is the exact triangles between 2 SHI of well, one is for gamma n minus 1, and the other is for gamma n. And the third space is I shop of the ambient 3 manifold S3. This is because when we take the zero surgery on the curve mu prime, we will get KHI of the unknots, and so this is isomorphic to I shop of the ambient 3 manifold. And this is how we relate the SHI with the I shop. And in general, we can change the basis on the boundary. So in particular, we take mu hat to be lambda minus m mu and lambda hat to be minus mu. And then we can define the suture gamma n hat similarly. So this is the suture consisting of 2 curves of slope minus n. So minus n means the homology class is minus n mu hat plus lambda hat. Then we can still consider the surgery exact triangle on the mu hat prime. Then so the first two are similar, and the third thing is I shop, but the space but the 3 manifold becomes the M surgery on the knot K. And this is how we understand the I shop of the large surgery by these two SHIs. Okay, and we also used another exact triangle, which we will call bypass exact triangle. And the general statement is that we consider three sutures on a three-manifold M, so that they are the same. They're the same except in a disk. So and all three sutures intersects the boundary at 6 points. And in the disk, the suture looks like this. So so the bypass exact triangle says we have a long exact sequence between SHI of those suture manifolds. But note that we should reverse the orientation of the three manifold and the orientation of the suture. So this is why in the statement of the main theorem, we need to add some minus signs. And in our special case, we will take M to be the knot complement and take the suture gamma mu and gamma n to be the sutures of slope mu and slope minus n mu plus lambda. So here the slope mu means well, we just take the 1/0 slope, which equals to infinity. And then we can apply the bypass exact triangles on these sutures to get the following two exact triangles. So the triangles are in SHI of gamma n minus 1, gamma n, and gamma mu. And the other triangle is also for gamma n minus 1, gamma n, and gamma mu. But the maps are different. So for the maps in the first exact triangle, we call them positive bypass maps. And for maps in the second triangle, we call them negative bypass maps. So those are bypass exact triangles we will use. And moreover, we can show that these bypass maps are homogeneous with respect to Alexander gradings. And moreover, we can also change the basis on the boundary so that we can replace all gammas with gammas that with some hats. So these two triangles, surgery exact triangle and bypass exact triangle, are two main inputs. We have. So and then I will introduce a geometric way to understand these exact triangles, so that we can understand these things better to get the construction. So this is based on the immersed curve invariants in Higgs theory. So the general setup is that for a three-manifold with torus boundary, and we have border floor homology constructed by Lipschitz, Auschwitz, and Thurston. And later, Hanselmann, Rasmussen, Watson constructed a set of immersed curve invariants on the boundary of M minus a point, which is denoted by HF hat of M. And this is indeed can be regarded as objects in some Fukaya category of the boundary of M minus a point. And for border floor homology, we have a gluing theorem. So the gluing theorem translates to the following facts. So if a closed three-manifold Y is obtained by gluing two three-manifolds along the torus boundary, then the dimension of HF hat of Y equals to the dimension of the symplectic floor homology of these two objects in Fukaya categories. And well, in particular, it is just the geometric intersection number of these two sets of curves. So in our case, we just take M to be the knot complement, and then I will draw some examples about curve invariants so that we can recover the href hat of the R surgery and href k hat of the dual knot. This is the dual knot of the dual knot in the surgery manifold. Okay, so maybe let me draw some draw example for the trivial. So this is the curve invariant. This is href hat of S3 minus the trivial, and usually it is cyclic on the horizontal direction, and it is bounded on the vertical direction, and then we can use this curve invariant to compute various Higgs-Floor homologies about these three manifold with torus boundary. So first, maybe let's just consider href hat of the knot, of the trivial knot, and in the Alexander gradient. So to compute this, we just need to find a curve. We just need to find a line that passes the base point and then count the intersection number. There are three intersection number and in different Alexander gradient. So we will find that this is one-dimensional. This is one-dimensional in the Alexander gradient 1 and 0 and -1. And then if we want to compute the dimension of href hat of the ambient three manifold, then we just consider a line, a vertical line that does not pass the base points. So and we will find there's only one intersection number, and this is one-dimensional. Then if we want to consider the href hat of the one surgery on the knot K, on the trivial knot, we should consider a curve. We should consider a line of slope of slope 1, so that we can find there's only one intersection number. This is also one-dimensional. And we can also compute the dimension of href k hat of the dual knot, maybe in Alexander gradients. So for this, we consider a line of slope 1 that passes the base point, and we find that there are three intersection points. So this is one-dimensional in each Alexander gradient. Okay, and for any other slope, any other surgery slope, we can just take a line of slope R. Well, and if we want to compute HF hat, we need to consider the line that does not pass the base point. And if we want to consider compute HF k hat, we need to consider the line that passes the base point. So this is a good picture to understand HF hat and HF k hat. And then let me use this picture to understand the exact triangles I mentioned before. So first, let's consider the bypass exact triangle. So the bypass exact triangle is a triangle between gamma I minus 1, gamma n, and gamma mu. So so here we just take gamma 1, gamma 2, and gamma mu. Remember that gamma 1 corresponds to a line of slope -1, and gamma 2 corresponds to a line of -2, and gamma mu corresponds to a line of slope infinity. And we can find that these three lines or three arcs form a real triangle in the universal cover of the boundary. And moreover, there's no base points in the interior of the triangle. And then if we consider the mapping cone of this map, then roughly speaking, it is just smoothing the corner here, and we will get a curve looks like this. So this is isotopic to the curve here, and then we will find that well, this is the geometric intuition why we have bypass exact triangle between these three sutures. And indeed, we can understand the positive and negative bypass exact triangles by these two different real triangles in the universal cover. Because when we fix the slopes of three arcs, there are two choices of triangles, and we understand one of them for the negative bypasses and the other for positive bypasses. And we can also change the basis so that we get a different exact triangle. So here we just consider the mu hat to be -2 mu plus lambda, and lambda hat to be minus mu. And then we compute the slope of gamma 1 hat, which is just mu minus lambda, or -1, and also the slope of gamma 2 hat, which is 3 mu minus 2 lambda, or -3/2. Then if we draw the arcs of those three slopes, we can find these three arcs also form a real triangle in the universal cover. So we know that these three things, there is also an exact triangle between these three spaces. So that's the geometric intuition for bypass exact triangle. And for the surgery exact triangle, first we note that it is not homogeneous. The maps is not homogeneous with respect to Alexander grading. So we should draw all spin C structures correspond to all Alexander gradings about the suture gamma 1, which means we should draw all these arcs together and also draw all these arcs together for gamma 2. And then we can consider the maps, the map here, the map F, roughly speaking, be the summation of all these maps. And then if we take the mapping cone of this map F, roughly speaking, we will get a curve that is isotopic to this curve. So we smooth all corners to get this curve. And yeah, it is obvious that this curve is isotopic to the vertical line. So that's why we will get I sharp of the ambient Riemann-Manifold by this bypass exact triangle, by this surgery exact triangle. And this is a geometric intuition for surgery exact triangle. And is there any question for these pictures? All right, so then maybe let's go to the construction of the differentials. So the construction is based on the bypass exact triangles. So we just put all bypass exact triangle about the positive bypasses together, just these triangles like this. And remember that the bypass maps are homogeneous with respect to Alexander grading. So indeed, we can calculate the grading shift of this grading. And indeed, the grading shift of this map is just 1. And we define this map to be the differential D1 plus. And then we can consider this map. So this is the composition of this map and the inverse of this map and this map. So well, here we will take the inverse of this map, but this is indeed well defined on the homology of D1 plus. So we call this differential D2 plus. And moreover, we can define more differentials, for example, like this. So this is D3 plus. And we can prove the following properties. The first thing is these dr plus differentials are independent of the choice of n. And secondly, if we sum all differentials together to get a differential d plus, then d square of the square of plus equals to 0, which means it is a real differential. So, and the third thing is we can calculate the grading shift of Alexander grading for each dr plus, and it turns out that dr plus increased the Alexander grading by r. And finally, we need to show that the homology of this chain complex is isomorphic to I sharp of the ambient Riemann-Manifold. Okay, and maybe we can look at the picture to understand why we need to define the map like this. So here is an example of curve invariant, and if we take a line of slope infinity, we will get five generators, which correspond to this five-dimensional space. And for D1 plus, we can consider the composition of this map and this map. So roughly it's this map and this map. And this is, this will count the bigone here. This will count this bigone. And which means we will get a differential from this generator to this generator. And for the map D2, it is the composition of this map and then the inverse of this map and finally this map. So we will, so the composition is roughly this thing, and we can find that it will count this bigone. And then we will get a differential D2 plus from this generator to this generator. And similarly, we can construct differentials dr minus using negative bypass maps. And then we can find the differential correspond to these two bigones like this. So that's why, well, that's how we find the definition of the differential maps, just by understand better from the curve invariant. So, and finally, let me sketch the idea of the proof for the large surgery formula. So the first step is that we, we consider a large integer m and take the mu hat to be minus mu plus lambda. Then we can calculate the slope of gamma 2 hat, which is 2n minus 1 over minus 2. And indeed, this slope is large enough, so we can use the middle Alexander gratings of this SHI to recover the information of iShop. And then for the second step, we find that there is an exact triangle between the space for gamma m minus 1 and the suture gamma 2 hat we just defined. And indeed, the map here is the composition of this map and this map. So this is a map from gamma m to gamma mu and gamma mu to gamma m minus 1. And in the third step, we use some algebraic axiom. So we use the octahedral axiom to prove there's an isomorphism between the homology of the band complex and the homology of the cone of this map we just defined. And then by step 2, the homology of this cone is isomorphic to the homology of gamma 2 hat. And by step 1, we can recover the information of iShop in this suture homology. And well, there are also some further directions which we are still working. So so the first one is what I mentioned before, is the mapping cone formula. And maybe we can also recover the border flow homology and inverse curved invariants in instanton homology. So these are all things I want to say. And thanks for your attention.
Well, are there questions? I'll ask one. So to what extent would knowing that you had a bordered version of instanton floor theory show, how close would that come to showing that it's the same as the Haggard floor? And once you get enough algebra, are you going to get that they're equivalent?
Right. That's a good question. And indeed, what we are still doing is that we want to construct the border theory by the bypass maps. And and I think maybe it's good to first understand better for mapping cone formula and then do something about border theory. Does this answer your question?
Yeah.
So do you expect the mapping cone formula to be a route to showing that I sharp of a surgery on a knot is isomorphic to H of hat of a surgery on a knot?
Yeah, let's see. So indeed, even in Higa floor theory, the application of the mapping cone formula needs some assumption because well, usually we will consider knots in Lspace, and we expect that the mapping cone formula can be calculated for the any surgery, I sharp of any surgery on floor simple knot in an Lspace. So because the differentials are not easy to compute, so we need to assume some special case. For example, there's the floor simple case, which means there's no differentials, and then it will be easier to use the mapping cone formula to compute instanton floor homology.
Yeah, you might have mentioned this already, but do you know how the differentials behave under connected sum? Or
yeah, that's a very good question, and I think that is the main thing in the proof of, say, the gluing theorem of the border theory, because Ashras and Szabo so we can when we splicing to manifold, and this can be understood by integral surgery on the connected sum of some knots. So if we can understand the connected sum, the connected sum formula and the mapping cone formula, then we may get the gluing thing for the border theory. But now I think Sudipta and Zemke are still working on this program, and yeah, I think we need to understand more about the connected sum formula for differentials. Now we only have connected sum formula for on homology.
and does one know the differentials on the surgery core after you've? So I guess you can.
Oh yeah, that's right. That's so if one of the knots is floor simple, so well, in particular just the core knots of the core knot in Lspaces, we already get some partial results that's about the differentials on connected sum.
Okay.
But the main thing about proving mapping cone formula is to work out the algebra. So we want to just prove the mapping cone formula by algebra and understand more about the behavior of differentials d plus and d minus.
Yeah, thanks.
I know it's very late in China, or very early in China, and it's late in the semester here. If there are not further questions, I can thank Fanny again. You can thank them even if there are. We will be back in 2 weeks with another GTV.
Thanks. Nice talk.
Thanks for the talk. It was great.
Thank you.